my goal this afternoon is to, by dragging you through the innards of a project that Todd Probsting and I have worked on for the past year, I suppose. And maybe after you leave the day, you'll want to go off and do some tricks with our compiler. Let me start by first going over a little bit of why we did this. One of the reasons, perhaps the two most important reasons, is we like to experiment with language design, in particular thinking about new language design ideas. And the C# gives us an opportunity to perhaps get in some new language features in a programming language that will see wide use. And Todd has already actually gotten one in. I won't actually talk about it today. So, the nice thing about this is the .NET stuff provides almost everything we need to do this kind of research, except for one thing. We need a compiler to actually try out language design ideas, and we need one that's got all of the right attributes, so we spend more time doing research than building infrastructure. We need something that's complete. We want to have a full C# compiler, but that's easy to understand, easy to modify, and runs fast enough to make it suitable for experimental purposes. And this, in fact, is what we built. In case you want to get out before the hour and a half has ruined your life, here's the results. We have a research C# compiler. It's called LCSC. It's written in C#. I think it's reasonable to believe you could understand it in about 1 or 2 weeks or so if you actually sat down with the code. Maybe a little longer than that if you're not a person who spends their Friday and Saturday nights reading compiler books. It's not very big. As you see here, there is about 13,000 lines of what you would call the compiler proper. That is these first two. So I get this to work. These first two lists here. The first one gives the line count as of today for the parser, lexer, and the data structures. Yeah, Gideon?
Maybe I'm jumping the gun, but if you can do a decent compiler in 20,000 lines, where do these 500,000 line compilers come from?
I've never understood that, except maybe it's the optimizer. But
I mean, this is a compiler to .NET, not to machine code. There's quite a bit that goes on.
This compiler does no optimization, right?
Yeah, well, I don't do optimization.
Neither does the product. I know. I claim it does, but
What I'm saying is there's a spectrum of what compiler means.
Yeah, there is a lot of code
What we
missing.
mean by compiler, and historically it's meant something bigger.
This is Swiss count 3 times bigger.
So anyway, the 6,700 lines are for the parser, lexer, and data structures. These next 6,900 lines are the passes that you need for what I will call a normal compiler. That is, if you want to compile C# to MSIL code. And you'll see as we go on, you don't actually need these if you're not really interested in using the compiler as, quote, a compiler. Now, there's another 5,000 lines here of some other passes that do interesting things. And I'm going to spend quite a bit of time talking about those. And then we have a few small program generation tools to help build the compiler. And I'll say, as you've already figured out, there is no optimizer in here, but you could put one in. I won't be doing that because I have a perfect track record of never writing an optimizer. Typically, small tools you might want to write I'd say run in the order of hundreds of lines of code. If you want to write a small tool that does something with C# code, figure it'll take a few hundred lines. A complete pass of some kind typically runs thousands of lines. Each of these, as you'll see here in just a minute, this is about 4 passes. So you're talking about a few thousand lines per pass. And we haven't done a lot of language extensions. We've done some, and they run a few hundred lines, maybe a thousand. But of course, you could get as big as you want, depending on the kinds of things that you want to do. Now, I advertise the compiler as suitable for doing language design work. However, it turns out that most people, including us to some degree, to date have not used the compiler as a traditional compiler or as one suitable for language design work. Most of the effort so far has gone to using this as an infrastructure for building C# tools, and I'll talk about that a little bit. Okay, so here is, you get far enough away from the compiler, what does it look like? There's actually not a whole lot to it. Parser reads in C# source. It builds an abstract syntax tree for its input, and then subsequent passes modify that AST by making a walk, usually a recursive walk over the AST. There's no fixed set of passes. There isn't, in fact, anything fixed anywhere. You get to say which passes you wish to run in the order that you wish to run them. There is no pre-specified output or output format. So the idea is that it's pretty easy to piece part together the pieces of the compiler that your particular project is interested in. We have a few tools. We have a parser generator. We have a little program that produces skeleton code for each of these passes over the abstract syntax tree. And we have a little program that produces strongly typed lists. So if you need a list of ints, there's a way to produce a list of ints. So you don't have to type all of that. So that's basically all there is. Input code, build an AST, and then do whatever you want to do to the AST. Now let's actually go through a little bit of these. Let me talk a little bit about the parsing. Todd has built a generalized LR parser generator, which takes a grammar, possibly ambiguous, that produces a C# parser. It accepts C# source code, builds the parse trees, as you all know. It'll build more than one parse tree if the input is ambiguous. You get to write a little bit of code to pick the right parse tree. Once you have picked a parse tree, we then will produce code that will take that parse tree and convert it. We'll build from that parse tree an abstract syntax tree. There's, again, not a whole lot to that. You have to do a little bit of work if you're actually going to, say, add language features whose syntax is ambiguous. The actual grammar has a little bit of interesting things about it. One is we tried to follow the C# grammar as it's published, so our grammar is a bit big. Interestingly, we use as our input format an Excel spreadsheet. And the idea here is that that takes away some of the parsing of the grammar for the parser generator, because things are already in columns and rows and things like that. And we actually use the Excel formulas in order to get the types of various non-terminals right. And I can actually show you what that looks like. We'll see if this actually works. Let's see. There it is. So here is our C-sharp grammar. I don't expect you to actually read this, but I'll give you a little bit of an idea. If you've used Yak or things like that, you'll see this is pretty close to the same. Left side is the non-terminal. The B column is the corresponding right-hand side of the production. The C column is the type of the non-terminal. And the D column, well, this one over here, is the action to build the abstract syntax tree for that production. And I've highlighted the if statement because it's the one that we all know. If statement is an if, Boolean expression, so forth. And way over here on the right-hand side, there are some new statements to build the abstract syntax tree node for the if statement. We use the Excel formulas to actually fill in column C here. So you only have to give a non-terminal and its type once. The rest of them will be filled in. One nice thing about this that's not instantly obvious is that you can add columns to do whatever you want to, and it won't affect our tools because they are only going to look at, in this case, columns with particular names, the first 4. It's turned out to work out handier than we thought it would be. Okay, let me go back to the, yeah.
So how many productions does this grammar actually have?
Well,
Just curious.
so curious? Let's go down and look. 476. Not our fault.
Not so bad. We did one for VB recently that's 1,800.
1,800. There's a good reason not to use VB.
Okay. I was wondering, is that everything done by hand, or do you have built-in support for things like? Is this just expresses in BNF, or are you using some form of extended BNF that gives you?
We do have support
and
for
epsilon?
lists. We do have support for optional elements.
Okay, yeah, that would make
We don't have any support for lists. We have
We don't
support for optional.
Option.
It's
Yeah, I'm
right
sorry.
there in the middle, switch sections.
Yeah,
subscript
right there.
opt.
See that switch section's op?
That means
so
it's optional there.
So you don't have to write the two. You didn't have to write
Or what?
two production.
That's the only thing we have.
That's the only thing
Right.
we have.
So that gives you a factor of 2 when everywhere you have epsilon.
Right. Basically,
Just
I wanted to be able to
yeah.
cut and paste the grammar out of the specification appendix. And they used op, so I
you
used
used
op.
op.
They didn't use list, so
I did use list. David?
So is the grammar actually ambiguous, or is it just that your LR parser doesn't find the...
The grammar is actually ambiguous.
The grammar is ambiguous.
For instance, the if statement is ambiguous. If you have embedded ifs with the dangling else, is the else combined with the innermost if A, if B, else C?
Are there semantic rules that come with it which do the disambiguation?
You're always no. It's actually a syntactic rule. You're supposed to take the one that's closest in, the tightest binding, and you can write a grammar that encodes that, but the grammar is hideous. And so what they chose to publish was the ambiguous grammar with some prose that said pick the.
Okay. Now, I hinted that we build these the abstract syntax trees. That means in order to use our compiler, you really have to understand the vocabulary therein, as you have to understand what those ASTs are. It's not particularly huge. There are 164 different node types. 16 of those are abstract things like statement and expression. The class hierarchy follows the C# syntax relatively closely, and it is strongly typed. That is to say, we didn't use object where we knew we could use a more restricted type, or we didn't use AST, the root type, where we knew we could use a more restricted type. And on the slide here, you see the class declaration for the if statement node that I showed you in the previous slide in the action field of the grammar. Again, relatively obvious. It has an expr, a then part, and an else part, and it has a constructor that is called from the action field in the grammar to build the AST, and does sort of the obvious thing. I'll come back to this in a bit, but this annotation down here, this may be null, annotates fields who, for valid C# input, might be null. And we use this in some of the program generation tools later on in order to be able to tell whether we need a test there. And I'll come back to that. You'll actually see that. I'll also come back to this last thing on the slide, the visit method. We also, as I indicated earlier, have a little strongly typed list program generator. Again, there's not anything particularly deep there. Let me see if I can show you what I'm talking about. Here is the, in Visual Studio, is the part of ast.cs, which is the file that contains all these. This is the AST for a class declaration. And you see here that the body is a declaration list. That is to say, it's a list of nodes of type declaration. Whereas if we just use, say, an array list, it wouldn't be as strongly typed. There's nothing particularly deep going on here, but it has helped us avoid some errors. Okay. So when I say it takes about 1 to 2 weeks to understand the compiler, it's really understanding these AST nodes. And once you get the first 10 of them, the next 10 are easier, so on down the line. Now, I said that once the ASTs are built, everything that's left to do is done by making passes over the abstract syntax tree for your particular input. Now, we have 2 ways to do this, sort of the easy way for quick and dirty tool-like things, and sort of the hard way if you wish to actually build new passes for the compiler. The easy way is done with this built-in visit method that is on each AST. And the idea here is you supply a 1 or 2 delegates and pass them to the visit node of the root of the AST, and it will walk the entire AST for you, and you'll be able to be invoked on each AST node. And the idea here is that you can pass either both a prefix and postfix, and that'll tell you whether you're going to visit the node in prefix or postfix. And so what is on the slide here is the visit method from the if statement node I showed you on the previous slide. Just goes through the various fields, visiting the node either in prefix or in postfix, and then recursing down. This is all built in for you. You don't actually have to write much code. You just have to write the two delegates that you pass in to do whatever you want to do with the node. Now that's the easy way. The other way is to write a complete AST traversal on your own. You might guess if there's 164 node types, that means you're going to write about 164 routines. And I'll actually show you some of those. First, however, let's look at a couple of simple C# tools that you could write using the the easy way, that is this visit routine. So the way that you typically write these is you write yourself two static methods. In this case, I've just called them prefix and postfix. You post your inputs by calling post. And if there have been no post sales, you'll get a non-null AST, and you simply hit it with new instances of the built-in delegate with prefix and postfix. So if you know C sharp, okay, you'll see this is not a whole lot to this. Now, the nice thing about this is that these tools can consider a context. That is to say, you can easily write a tool that will say, look for only a particular kind of node in a particular context, because you've got an AST. So unlike text-based tools, it's pretty easy to write a little tool to poke around and see what occurs in a particular context. It's easy to do things like compute things like the maximum nesting depth of if statements, so you can holler at SDEs that have 16 levels of nesting. Let me actually show you one of these because it's so small it fits on a view graph. This is due to Rooston, who I can shoot with the laser right there. Suppose that you're interested in knowing how many occurrences of if something throw occur in your program, because it looks like it might be an assertion. You like to actually find this pattern in your code. Well, you could write a relatively complex grep expression to find that, but you might not get the context right. It might not work if throw isn't on the same line as the right parent and so on. But you can see that you can write a delegate, or this routine that I've written up here, to do it pretty easily. That is, if you have an AST and it's an if statement, and the if statement's then part is a throw statement, and the else part is null, then it looks like this pattern. Boom, you say it's a possible assertion. And the way you do that is, again, using the same pattern I used on the previous view graph, is to post your inputs, and then go ahead and visit the AST with an instance of this delegate type with do it as the function. You'll notice here, by the way, I only passed one delegate. If you just pass one, we assume it's a prefix, so you don't have to actually write the null empty delegate, or the delegate that doesn't do anything if you just want to do a prefix pass. Now, I can actually...
Before you go on, I want to say one quick thing. One of the things we tried to do in the compiler is sort of, to the best of our ability, anticipate any possible use, which meant we tried to throw away no information at all. And one of the things Dave didn't point out here is in his console.write line, there's ast.begin.
Oh, yes.
Every one of our AST nodes has, when it's built, the source coordinate for the beginning and ending of that construct stuck in there. So we're maintaining all kinds of information, and there's bloat and all that. But that means you can report exactly where it occurred.
And that's what you'll see when I type the next
but I just want
command.
Any information we ever commute, not just source level coordinates, type information, we hang on to it forever, so that some future pass that may want to investigate it can.
So let me actually run this one. Pardon me if I have to do a little bit of typing. So here is the program. See if this actually works. And I'm actually going to run this on all of the modules in the compiler, except tables.s, which I'll explain, tables.cs, which I'll explain why in just a minute. Now you're seeing that at line 55 in types.cs, there is this pattern. And in line 9 at character 4, there's also this pattern. Now, tables.cs is the output of the parser generator, and it's pretty big. So I didn't want to make you all sit through that. It's gigantic. Okay. So you can see these kinds of things are pretty easy to write. And we've had actually quite a few people write little things like that. I've actually thought about, for example, coming up with a little language of specifying tree patterns, so you don't actually have to write the code. However, anything I've come up with so far, the specification of the tree pattern is about the same length as the code. You might as well write the code. Okay, now the, quote, hard way is to write a full-blown visitor that makes a pass over the AST. And our AST visitors is any class with a public static method with the arguments you see there named visit, takes an object AST in and a text writer, and its purpose is to do something to the AST, we don't care what, and then pass back potentially the new AST. So this, you take an input AST, do something, return that AST. If you do some output, we likely like you to write it on this text writer here, because we can actually set up some options for you. And as you'll see in a bit, you can stack these up. So you can have one visitor that does something and passes the AST down to the next one, so on. And again, we don't care what they do. You can use ours. You can write your own. As you'll see here in a bit, you can intermix ours and your own. Eric, did you have a question? I'm sorry.
Yeah, I had a brief question. Just given that you were talking about your emphasis on strong typing, why are ASTs here typed as objects rather than some root?
Because it may not be an AST at some point. You might want to add a pass that creates some data structure that's going to go into one of your tools, and so.
Okay, so it's just for if you're building your own custom trees, you don't want to.
Right. We don't want to force you into our hierarchy. Now, the way that you actually invoke these is that when you actually run the compiler, you actually list which visitors you wish to run. These are typically in other DLLs. And the order in which you give them on the command line is the order in which they're going to be invoked. You usually say the class name and the file name. That's usually a DLL. You can, of course, leave that file name off if the file name is the same as the class name, so forth. And the purpose, of course, is for it to pass the do something to the AST and pass it back. Now, if you're going to go write one of these, and there's 164 AST nodes, you know you're going to have to write approximately 164 methods, approximately. You might write more, you might write fewer. And so there's a lot of boilerplate. Each of those is going to have to make recursive calls on the fields of its particular AST node that have other ASTs. So we have a little program that will basically produce the skeleton code for you, so that you don't have to write that. So you think if you sort of run this routine mic visitor, and it will produce most of the code. You just sort of fill in the bodies. And the arguments here are things that you'll see on the next slide. You can tell it the name of the class and the arguments that should be passed down to the recursive calls. This is the particular invocation I use to build a pass called bind. And I can show you this, what you get out of this thing using the important name foo. So here's what you get. You get a class with 164 methods in it. And the argument is the thing you saw on the command line. And if I move to the top, you would see that the class name is bind. And then what is in the body of each of these is the code necessary to do the recursive calls. So you don't have to do that. And so here's the if statement that I've been talking about. And here's where you can see way back in that earlier slide when I said we annotated some of the fields with this maybe null attribute. Well, here's where we use that attribute, in particular when the program knows the else part might be null for a valid C# input and produces the appropriate guard. So the idea is that then you would take this and edit it. Now, this is not a perfect solution because once you get this and edit it, there's no way to go back and reproduce it by running Mick Visitor again. But we found this sort of solves sort of 80 to 90% of the problem here. Saves an awful lot of work. Okay. How am I doing on time? Okay. All right. So let's actually talk about some of these visitors and what they do and how you might use them to do some language experimentation work. If you just want to look at the compiler as a traditional compiler, we have 4 passes. One is called bind. It binds uses to definitions of identifiers and annotates the tree with symbol table entries. There's a type check pass. That type checks the code, annotates the AST with types, methods, things like that. There's a rewrite pass, which basically cleans up some of the ASTs to make it easier to produce code. And then there's the IL-gen pass, which emits MSIL as ASCII text. We use IL-ASM to produce the actual exe file. And there's a little bit of a white lie here. Bind actually does 3 walks over the AST. The other passes just do 1 walk. But again, each of these passes you write, we don't care what you do. If you want to do 4 or 5 passes over the AST, that's okay. And if you invoke our compiler with no arguments or no -visitor options, this is what you get. So if you sort of walk up to our compiler, you can treat it as a normal compiler. Most people don't. Now, those are the traditional passes. I'm not going to talk about them in any detail. One thing I should point out, however, is that we do annotate the tree with some other data structures. So part of understanding our compiler, if you want to use any of these passes, would be to understand the symbols, the types, and so forth. And I'm sure Bruceson will tell you that's easy too, I hope. Now, it turns out we have more what I will call exotic visitors, things that don't really have anything to do with compilers per se. And in fact, there are more of these than there are the traditional ones. We have one called XML, whose sole purpose it is to emit XML for the AST. Suppose you want, for some reason, to transmit the ASTs somewhere else. We have a pass that will make a pass over the tree, produce a huge XML output, which you can send off somewhere else. When I write code, I like to put things in alphabetical order. It drives me nuts when stuff's not in alphabetical order. So I have a pass called sort members that takes in a C# program, alphabetizes all of the members in all of the classes. Once I have that, what do I do with it? Well, I also have a pass, should have done this in a different order. Also have a pass that takes the ASTs and emits C# source code. Right? So I just pipe my sort members followed by the source code, and I get my members alphabetized. So if you ever give me a piece of code, you're likely to get it back with the members alphabetized. We do throw away comments, by the way, so I also get rid of those. There's also a visitor called CodeDOM. If you're familiar with the code document object model used in the web services stuff, you will know that that you can write a code document object model program to produce what amounts to an AST for a program. And we have a way to take a C# program in and produce as output the CodeDOM program that will build the CodeDOM for that input. Did I say that right, Todd? Yes, I think I did. Okay. You could, for example, add a different back end. If you didn't like producing ASCII MSIL and you wanted to produce the binary EXA file, you could add a new code generator. Now, perhaps the most interesting two for purposes of understanding what's going on are display and browser. Some of these, in particular source, display, browser, all just take their AST and do something and return their AST. And so that you can insert display and browser into, and to some extent source also, in between any visitors and perhaps get some help. And you'll see that help on the next view graph. In particular, display displays all of the data structures, including all of the ASTs in HTML. So you don't have to add write calls to debug your program. You can just browse the data structures. Browser is Todd's better version of that, which you'll see you can correlate source code with ASTs and MSIL. And I'd like to actually show you both of those. Along with a couple of these others. So let's just actually see some of these. So if you want to emit XML for the program Hello World, you would just use a command saying invoke the XML. So let me actually do that. I'll also do the next one, the print source. So here's my command. All right. Stand back. I won't make you read all that XML. I actually went to a talk once where the guy did his slides by typing XML. It's quite painful. So there you see that you can get the XML. Pardon the typing. And here is the source visitor, which will, as you might guess, simply show you the source program. The little annotations you're seeing here are just telling you how long each pass is taking. Let me pop back to that. Oops. Yeah. I won't bore you more with the alphabetizing pass, but I do want to show you the last one on the slide. Suppose you're trying to debug bind. You're trying to understand my pass bind. Well, one way to do that is to simply run bind, follow it by invoking display. Here's a case, by the way, where the actual display class is in a different named file name, so we have to give both. I won't actually run that because I actually already have it up here on the screen. Let me show you what you get. you get a hyperlinked set of data structures. And in particular, the code that does this doesn't care that it's coming from my compiler. It really could display any set of arbitrary data structures. So the first thing you get is the root of the AST. In this case, a compilation that has its inputs a compilation unit list, which happens to be right here, and a compilation unit happens to have a declaration list, and I'm going to go ahead and click that, and it has a class declaration for that main, and the class declaration has a body, a declaration list. It has a method declaration, so on. Now, you were trying to figure out what was going on with that bind pass. Well, the bind pass, for example, annotates nodes with symbols. And so here is the value that's been annotated by that node. You could click that. You would go down and see the method data structures. It's often easier to do this to understand what's going on with the data structures than reading the code. And way down in here, you can see that there's the main. And of course, it's hyperlinked, so you can back up. You go back up to the class. You see here's its class type. And you could go follow class type, look at those fields, so on. So it turns out this is a pretty nice way to debug symbol tables, or symbol tables, ASTs, data structures that you might get. And this is the way we actually find most of our errors, by going and see, oh, this node doesn't have the right type or the right field attached to it. Okay, well, browsing HTML can be slightly painful. In particular, if you compile a non-trivial C# program with a lot of hooks into system.mumble, you will get a pretty big HTML file. A 6 megabyte HTML file is not out of the realm of possibilities. And it's also a little hard to correlate the piece of the AST with the source code it came from. You like to be able to say, gee, where did this if statement come from? Well, you've got the coordinates in there. You've got the line number and so forth. But you like a little bit of help. Todd's browser basically does that. It allows you to reveal, instead of having to look at all 6 megabytes of the data structures, you get to reveal just those that you're interested in. In particular, in particular, just those that you click on. Also, it correlates the AST nodes with the actual source code. So if you were to invoke Todd's browser, which is called browser.browserVisitor, on hello, you'd get what you see in this next demo. Is that the right one? No. That's the right one. So here's our input, hello.cs, and as you saw in the earlier view graph, the root node is a compilation unit. Actually, there's a slight difference here, but I'm going to gloss over that. So I could open this up and see the fields just like you saw it on the previous view graph, on the previous slide. I could go down to declaration list and click that, okay, and you'll see you'll begin to see the declaration list. I could go down here and click the class declaration. Now notice when I did that, on the left side it highlighted the class hello. So as you might guess, the actual AST node you look at is correlated to just the code that it corresponds to. Now, you don't have to walk down it this way. As you saw me on the previous HTML slide, I really had to sort of walk down it. I could go over to the left side and say, look at that string constant and just click that. And what I see on the right side now is the node for the string literal. That's also an AST node. And if I open that up, you'll see somewhere down there it's the string hello world. So you can sort of navigate along. And this parent button up here, if I click that, it'll walk up the tree. So if I click that, what happened? Well, notice that, let me point this out. Notice that this side didn't change at all. That's because the string constant is a child node of an argument node, as you might expect. And I could keep walking up. Anyway, now I get an invocation expression down here at the bottom, so on. So this makes it a lot easier to navigate through the ASTs when you want to focus in on just one part of the code. Again, you're going to try and understand the compiler. This is a pretty good way to do it. Okay. Questions? Todd, you happy?
Sure.
Okay. Okay, now, if you have one kind of browser, code browser, you might as well have more than one. And Todd has two others, one for CodeDOM, which I won't show you, also has one for MSIL. That is, there's a way to browse the MSIL and correlate it back. Again, you can see what's going on here. In order to invoke this, you invoke bind, type, check, and then his browser will invoke the ILGen for you. And this one is actually even handier. See if I can get it. So here is a slightly larger program, 8 queens. And its source code is in the left window. The generated MSIL is in the right window. So, for example, if I go down to this string constant way down here, which I don't think you can see the mouse, I'm going down to that string constant right there, and click just that, you see on the right side the load string MSIL instruction. Again, I can do the same kind of thing. I can go up my parent. Didn't really see any change there because there is no visible change by going up to the argument. Another click of parent, and you get the whole call. So you can see here is the code for the call to ms corelib system.console right with the stuff off to the right-hand side there. And it's pretty handy to be able to do this in investigation like this. Suppose, for example, that you really wanted to see how these amp operators are done up here in the if statement, which is always entertaining. I actually, of course, didn't get this right the first time I implemented it. So we could start up here anywhere. There's rows. That's not quite enough. We want to see a little more. So we can go to our parent. And there's the first operand, the first sub-expression. And you can see what's going on is it's loading rows sub-r and branching if it's false to the label $13, then loading up sub-r, c, subtract, add, so on. So it's a way to explore the code, which can be quite voluminous without having to look at the whole thing. Okay. Okay, now, I started out by saying we wanted to use this as a way to experiment with language design by adding new language features. So I guess I ought to spend a little bit of time except on the toys on some of the research use. Well, let's look at one language extension. Suppose you want to add type switch. A type switch statement is a lot like the modular 3 type case. It's a case statement on a type of a value rather than the value itself. So in particular, I proposed the syntax at the top here. You see the idea is that I'm going to do a type switch on O. If it's an int 32, I want to execute this statement with X being the int 32 value of O. Likewise, if O is a symbol, then I'm going to execute symbols.add with S, where S is O cast to a symbol, so forth. There's also a default case. And this abbreviates the typical if-then-else chain that you see this done. That is, if I had to write this by hand, what would I do? Well, I'd do an if, then I'd introduce a local, cast it, and use X, so on down for the other ones. And so the type case, the type switch abbreviates this if-else chain, and it also makes it a little bit easier to introduce these locals and provides the typecasting for you. Suppose you wanted to add this and use our compiler to do that. There's two ways. One is the easy way. The easy way is if you happen to have an extension that you know can be expressed in terms of C# source code, then there's no need to do anything else but get the right C# source code out the other end. You can do a so-called source-to-source transformation. Now, in this case, you saw that all this is doing is abbreviating an if-then-else chain, so we could do it this way. So what do you have to do? Well, you have to do 3 steps for this usage. One is you've got to add the grammar. You've got to add the type switch grammar. You need to add some AST nodes to support the type switch. You're going to build new type switch nodes. And then you need to add code to produce C# output when you actually want to produce the output. You can do so by extending source.cs, that the visitor I told you about earlier, that prints C# code from ASTs. Now, it's important to know you don't have to write, you don't even have to touch source.cs. You simply extend it with the new node types that you add for type switch. So I can actually show you each of these. You can see this took less than 100 lines to do. Let me start with the type switch grammar. Here it is. There's not a whole lot to it. And you can see by the 4th column, which we call is the actions to build the AST, that I'm going to build some new AST types, type switch underscore statement, type switch section list, so forth. So I've defined those somewhere. And I simply add this to the grammar. I don't have to touch our C# grammar. The program generator takes an arbitrary number of Excel files, probably some upper bound, and just goes ahead and produces the parser for that. So there's the first thing you had to add. The second thing you had to add was you actually had to write some AST nodes. That's here, those AST nodes you saw on the previous graph. I've added type switch label, type switch section, type switch statement. Again, you don't have to edit our code. You can simply add this to the compiler. And then finally, you need to extend source.cs by building a type switch.cs. So you see what I've done here is to have a class type switch source and extended it. I didn't have to touch the code. I just need to add just those things that I need to override or add because I've added some new AST nodes. So in 100 lines, less than 100 lines, we've added the type switch statement, and I can actually show that to you. Right here. I have basically the source code that's on the slide in this file, and I'm going to execute. This is actually, I should show you this. Notice down here, I'm going to invoke my type switch source visitor instead of the source visitor, and I built the compiler with the type switch statement in it. And what you get is an if-then-else chain that's a little dirtier than the one you saw earlier because of all these made-up variable names in order to make it compile. But I'll go to the top so you see. So now what I've done is I have extended C# by using a source-to-source transformation, the output of which will compile with the normal production C# compiler. Yeah, question?
For that, the grammar may be ambiguous, and you might have to choose between different parse trees.
Right.
How do you choose between those trees?
You actually write a little piece of code to do that. I wouldn't call that elegant, but it's typically not very hard. And so in this case, the grammar was not ambiguous.
Right. In this case, it's not.
And so we didn't have to do that. What could happen often is you would actually write it the first time, find it's ambiguous, write the little code, or figure out how to make it not ambiguous.
I'm just curious. So, for example, what information do you have to decide which parse tree?
What do you have, Todd? You have
the parse trees.
You have the parse
I
trees.
hand you all the parse trees.
So I have to basically traverse the whole parse tree.
I'm sorry?
Do I have to?
No, I'm sorry.
The whole parse tree.
The ambiguity is isolated to the lowest point in the parse tree that's ambiguous. So let's suppose the if statement. It's not like I hand you two compilation units and say, please fix it. I hand you the two if statements and everything that's underneath them.
Okay.
And say, pick between these two.
Okay, it makes
So
sense.
you get them in context.
Right.
You get the actual point of ambiguity.
Okay, that's good.
Okay, so one way to extend it is to do, as I said, these three steps. We could have done this slightly differently, by the way. We could have built, instead of adding the type switch AST nodes, we could have simply built the right if-then-else AST nodes from the get-go. Okay, we could have actually gotten rid of step 2 and 3 there, the second two, if we had changed the actions to build something more complex. We could have done sort of a halfway. We could have gone ahead and built the type switch AST nodes and then had a pass that rewrote those nodes into if-then-else chain. So there's a lot of different ways to do this depending on how you want to do it. Yeah.
Did you do the binding and the type checking?
No, this one I didn't do the binding and the type checking. In fact, I'm glad you asked that because I should point out this is why this is also why this is the easy way. You don't have to do any of that with source-to-source transformations. If the extension you want to do can be done that way, can't be done that way, then you get to do it the hard way, the full nine yards, as I call it. Again, the code is not huge. I won't make you look at this code. In this case, I've had to extend every pass in the compiler. Right? Again, I didn't have to go in and edit them. I just needed to add code for type switch. So the first two steps are the same as you saw in the previous graph. The 19 lines for the grammar spreadsheet, the 63 lines for the AST nodes. Now I need to go in and extend bind with a new class type switch bind that inherits from bind and add just those lines to handle either the new type switch AST nodes or any other nodes that might be handled differently. For example, break statements need to be handled slightly different because they might break out of a type switch now. Right? And that took me 100 lines of code to do that. Now I need to go and take type check. This is Ruson's question, and write a type switch underscore type check class. And that takes a few lines. That I need the type check. Turns out that only took 35 lines. Likewise, I need to go down to rewrite, because each of these now has some new ASTs. So I needed to extend rewrite. That took 29 lines. And finally, I need to produce the code in the end, MS-IL code. Again, that took 65 lines. So now what I have is a compiler that will produce MS-IL. Yeah.
Wait, if I recall correctly, like a lot of those lines you can write on. Not only is it short, but a lot of those lines you just sort of write on autopilot. Like
yeah.
The rewrite.cs, you didn't have to think at all.
No, I didn't have to think very hard. I just had to add the new. In fact, I probably did a cut and paste and changed the name. Yeah. No, these for this particular language extension, it's true that many of those lines are not very hard. I won't actually execute this one because I already have it in the buffer. But here's the output if you care about looking at this output, and you see it looks a lot like this. Here's a type switch. There's a load, a store, some temporaries. There's the infamous is instance if you've ever had to use the is operator in C#. Right? So it turns out that even a full-blown extension like this, for some extensions, can be done relatively easily. That is, the idea of our compiler is to make it easy to do these kinds of extensions in a reasonable amount of effort. So you don't have to write a whole compiler to see if type switch is the right thing that you want to do. Again, we could have done this differently. I could have built the ASTs as if then else changed early in the process. Okay, so I hope I've convinced you of. It didn't even take an hour and a half. Is that what we have is a relatively simple C# compiler. It's at least relatively easy to understand. I think I can say for certain it's easier to understand than the production compiler, which was written in C++. It's easy to modify, or I should say usually what you do is extend it. And so far it's worked out pretty well for doing language design experiments and some language-based tools. You're all welcome to load this on your own machine. It's available in Source Depot at the port and location shown on the view graph. There's also we have a web page about the compiler, which is here. And at some point, these slides will be on our PLS website. And there's always a current snapshot located in the research public area. Questions? Yeah.
You showed as an example how to extend the syntax of the language with a type switch statement. You might also want to extend the language to add new types.
Yes.
That might involve not just local changes in the type check module, but more global ones. Have you tried that, or is that? Would you recommend
Jacob
it?
has.
Is it easy?
He has added future types to it. Some of the changes he made work like adding the type switch. He can just subclass. The types he's added are restricted to be used in mostly his new future statements. So he didn't have to go through and change the if statement, for example. If you were making an addition that basically touched everything, you have a lot more work to do. And if you make an extension that touches a smaller number of things, suppose you made an extension that was going to touch while statements and try-catch statements. Okay. You would need to subclass the passes and override the methods that traverse those ASTs. If you get to the point where you're overriding all of them, then you might as well take a copy of the pass and edit it. Yeah.
Can the compiler go out in source, or?
Well, it can be used internally in source. I mean, the source depot has all of the source. We have no plans at the moment to release it outside of Microsoft. Yeah.
About how long did it take to make the compiler?
Let's see. I don't know. Wall clock time. Probably a year. I mean, that spans a ski season, which all bets are off on. But about a year. I think that's right time. About a year.
And about how many team members?
You're looking at him. Except Todd did the parsing part, and I did all the other pass part. And he did the browser that you just saw. By the way, the browser was done, in about 2 weeks total. So we're not talking about a huge amount of code. Okay? All right, I'm going to go back and look at my source depot logs. I expect to see 24 downloads. Yeah.
Is there any plan to integrate it into Visual Studio? Or?
We don't have any plans to do that. Are you volunteering?
Suppose that you wanted to take, if you build some things, maybe a rewriter and so forth, but you expect that much of the input is not actually C# source code, but comes from MSIL. Do you have libraries that would read in MSIL and
we use, in fact, I should have said that. We actually use the Bartok metadata reader, which will read MSIL. We don't currently read. We don't really do anything with the MSIL part. Right now, we just read the types.
So in other words, it does not translate into the same AST data structure.
That's right.
We only use it to the point of types.
Mm-hmm.
Yeah.
In case you haven't heard, Microsoft doesn't like decompilation.
Can we use only the parser generator, or how would you compare this parser generator with to other C# parser generators? Let's say that I want to parse for a toy language or.
Well, Rooston can answer that because he's actually done it.
You just want to take a whole new language, or?
Right, for a toy language, or for a very small script language, or
So not related to C#.
Right. Not related to C#.
For that, you can use. Todd has 2 parser generators. One of which is used here, which is more like a traditional YAC.
Right.
Speaking for Todd here, but the other one, which is the one I've used for several smaller languages that I've used in various ways, combines the lexing and the parsing into one spreadsheet. That's the one that I've used there, and it uses the Excel spreadsheet looks much the same way. If you want to parse large pieces of source or expect it to be blindingly fast, then you want to do something different. But if you want convenience and get there fast, it's a fine way to do it.
Right.
Yeah, I should say the parser generator used for this compiler is only used for the compiler. It has no other clients. It wasn't built that way. I abandoned it afterwards to work on something that would combine the lexical stuff and the.
Well, it just looks very convenient because it's very close to YAC or this zone.
Well, it's okay. So I hate YAC, and because what happens with YAC is you grab a grammar from wherever, and then you end up changing it. Unless you were just lucky enough to have found somebody that's already published an LALR grammar, you end up changing it, and so now you're out of sync with the previous grammar.
It's an LI, LR.
This will handle any arbitrary grammar.
LR.
Any grammar, not LR. Any.
Okay, because we handle those like confusions, like those ambiguities, like.
I just hand you more than one parse tree. You can give me a terribly ambiguous grammar.
Give me a terribly large set of parse trees.
And I'll give you back a terribly large set.
Complexity
What's the complexity of what?
of parsing. I mean, it could be very huge, right? If the ambiguity is big, then you can get like exponential number of choices.
That's correct, which you would expect. If I promise you to hand back and all the parse trees and there's an exponential number, you can't expect me to do it in less than exponential time.
Yeah.
So don't write those grammars.
Okay. And also even like get choice, like just 3 choices, and this statement is although you only gave me this subtree could be very big. Maybe there's only.
They share all the nodes underneath that they can.
Yeah, but then it could be difficult to find what's the one we want.
Well, theoretically, yes, it's true, but in practice, when people write ambiguous grammars, they almost always give you a disambiguation rule. And the disambiguation rule is something that they assume you can apply, because presumably they had to apply it. So, with the if statement, it's that you bind as tightly as possible. I check that in 2 lines of code. I can pick between the two. There's 2 places where the grammar is ambiguous. The if statement, and then also casts. It turns out if you say paren, identifier, paren, +3, are you casting +3 to whatever that type is? Or are you adding the value of that expression to 3? It could be interpreted either way. And it turns out that the disambiguation rule in C# says that you're doing the binary operation. And so, the rule is you check the next symbol after the following paren, after the end paren, and if it's one of this set, then you pick this parse tree and you don't pick that one. And so when I'm handed 2 parse trees, I say, which one of you doesn't look right? And I grab it. I throw it away and I grab the other one. So, yes, you can come up with a weird disambiguation rule that would require investigating the entire tree, but usually you're just looking down at your children.
Well, I guess it's good for C#, but it won't be very good for languages like ML, where you can declare the associativity and the precedence of the operators.
That's true. We are assuming the rule currently assumed. Well, I shouldn't say it. The way we use it, we assume that all these things are disambiguated syntactically. But there's nothing keeping you from just creating an abstract syntax tree node that happens to hang on to both of the alternatives so that some later pass can disambiguate based on semantic information. And that's no work.
Okay.
I might just add one more thing about the Excel spreadsheet. Something I found compared to Yak or Java CC is that it feels funny to write these things in Excel to begin with, but then actually because what you end up doing in Java CC or Yak is that you write lots of code that sits around your grammar, and after not very long at all, your file is just a total mess. And what I found in the Excel spreadsheet is that it remains simple afterwards. You just have one column with the action, which I found quite convenient.
Oh, I didn't fully answer your question. I got sidetracked with the ambiguity question. So I abandoned this one to write the one that Ruston's now using, which combines the lexical stuff in. And it's even slower than this one. So if your desire is to have a particular fast parser, look somewhere else.
Right. I'm just interested for like small things, not more like experimental, like small tools, which is perfect.
Send me an email and I'll show you. It's also on the same source depot thing. It's just a different location. I can take what it is.
Okay. Thanks.
Thank you.